Welcome to this class. In this class, we will discuss on defuzzification methods. So, why we need the defuzzification methods? Basically, till now we have seen the evaluation of the rules which we have been formed to design the controller. So, we have seen using the Mamdani model that if I have, let's say, one or more than one rules, and with that rules I will be able to evaluate the rules to find out certain output for some kind of change in the input. Okay, so once I am evaluating the rule, then what is happening here is that I am getting the resultant consequence or the resultant output. Basically it is in fuzzified form, but in order to do some action, basically what I need the real value or I need the crisp value. So what I have to do, I have to convert this fuzzified value into crisp value or into real value. So this defuzzified value, that the conversion of fuzzification into crisp value is called the defuzzification, and this defuzzified value in fuzzy logic controller, basically it will represent the action which is to be taken to control the process. So there are so many methods are available in the literature for defuzzification, and here we will see some of the well-known defuzzification methods that can be used to obtain the defuzzified value. So I am going to list out the methods. First method called centroid of area, or it is again called center of gravity. Then second method is bisection of area. Then center of area. That is called bisection of area only, I'm sorry. Then center of sum. Then mean of max. Again I can call smallest of max. If it is the smallest, I can also call it as the largest of max. Weighted average method. Then maximum membership principle. Etc. Fine. So this will convert the fuzzified output into a single crisp value with respect to that particular fuzzy set. So let us see some details on some of the defuzzified method. So first we will just have a discussion on centroid of area, or again it is called center of gravity method. So we'll see how this method can be useful to convert this fuzzified value into a single crisp value. Okay, so basically this method provides the crisp value based on the center of gravity of the fuzzy set. Okay, so here area and the center of gravity, or I can call the centroid of each sub area, that is the resultant fuzzy area what I have, that can be divided into sub area, and from sub area centroid of each sub area can be calculated, and then sum all the sub areas in order to find out the crisp value. How? That is, let me call Z of centroid of area, or let me call z asterisk, which will represent the crisp value. Okay, and this can be obtained using this method as integral over some z with z into mu c of z with dz. C is the sub area or sub fuzzy set divided by area under the curve of this particular sub area, that is mu c z of z, which is in continuous domain. And in discrete domain also you can write the same, which will be the summation for these different sub fuzzy sets or sub areas, that will be zi into mu c of zi and divided by the area of each mu c of zi, where I will be equal to 1 to n. This will be basically for n sub areas. Okay, so this z will be acting as like center of area, area of that fuzzy set. Okay, let me illustrate with one example. So suppose let us I have two rules and two antecedents, and from that applying Mamdani fuzzy model, I would have been obtained the resultant consequence, let's say mu c bar dash of z is as follows. Suppose resultant, this is no need, it is not necessary that it is 1, because this is all clipped sub area or clipped area after evaluating the rules. So let me take it on z 1 2 3 7 8 and 9. Okay, so from that say this is middle of 7 to 8, 7.5. Something like this. Okay, so let me suppose this is my resultant fuzzy, the resultant, what we can say, the consequence or the output which has been obtained after the evaluation of fuzzy rules. Now what I did, I have obtained this in fuzzified form. Now basically I want to convert it into the crisp form. Okay, so and that is using method called centroid of area. So in this, what is to be done, you just divide this overall area into number of sub areas. This is in triangular or trapezoidal form, so it is easy for me, but if it is in Gaussian, then it will be somewhat difficult to compute. That I have to write the equations for that curve and I have to solve it. But now it is simple in triangular and trapezoidal form, so I can do it quickly. Okay, so let me divide this into number of sub areas. So suppose this is my first area, triangular, this second, one more triangle here is forming, say third, one more, so this is fourth, one more here, fifth, this will be sixth. So overall this area I have been divided into this way. Okay, so 6 sub areas. Now what I will do, I will find out the area of each sub area or each sub fuzzy set, and also I will calculate the centroid of areas, so that centroid will act as zi's and mu c bar of this zi will act as the area. Okay, and then I will sum up the things. Okay, so what is the values, what is the equation, that is z asterisk. If I am writing, just assume that it is crisp form, and if it is, if I am writing z, this variable in fuzzy domain. Okay, so crisp domain or crisp variable can be obtained using addition of zi into mu c bar of zi over addition of mu c bar of z. Okay, where I is equal to 1 to n, so n will be number of sub areas, zi will be your centroid, mu c bar of zi will be your area. Fine. So first calculate the area for first sub-region, let me call A1. So this is a triangle, so area will be half into base is 1 and 2, so base is 2, height is 0.5, so 1 by 2 into 0.5 into 2, so A1 area will be 0.5. What will be A2? A2 is now rectangular, so it will be 1 2 3 4 into 0.5, so this is 4, this is 0.5, so it is 4 into 0.5, which is 2. Then area of 3, again it is triangular, so it is half into base is again half, so it is 0.5 into height is 0.2, so which is coming out 0.05. Similarly calculate the area for fourth sub fuzzy set or fourth sub area, so which is 0.5 into height is 0.3, so it is 0.5 into 0.3, which is coming as 0.15. For A5 it is same, that is 0.5 into height is 0.3, so it is 0.15. A6 will be how much, again it is a triangle, sixth region is, so this is 1 and height is 0.3, so 1 by 2 into 1 into 0.3, which is coming as 0.15. Now I have to calculate the centroid of each area, and we know how to calculate the centroid of triangle, that is x1 plus x2 plus x3 and y1 plus y2 plus y3. So this way we can calculate, but here I am interested in zi, which will be giving me the domain kind of the centroid. So to calculate the centroid of areas, first let me calculate C1, which will indicate the centroid of this area, and that will be, let's say, for the independent values. So what is the independent axis value for first point? It is 1 plus second x-axis point 3 plus third point x-axis point, a point is also 3. Okay, divided by 2. How to obtain? So for the triangle I have x1 y1 point, this x2 comma y2 point, and this is x3 comma y3 point. So calculate the centroid, x1 plus x2 plus x3 divided by 3, similarly y1 plus y2 plus y3 divided by 3, that way you will get it the point. So this 1 plus 0.3 plus 3 will be 7 by 3, so now roughly I will say 2.3. okay, and this is 0.5 upon 3, so it is 1.15. Fine, so you will get something here. Okay, so for that what I need the value of the centroid for in terms of independent variable. So that is zi. So I got, let me call this is z1, which is giving me the x independent variable point. Then let me calculate the centroid or z2 for second area. So this is 3 plus 7 upon 2. So for second, what is the point? This is x1, this is x2. So 3 plus 7 upon 2, so it will be 5. For third sub area, what will be z3? Again, this is a triangle. So here 7, one point is 7, second point is 7.5, third point is also 7. Okay. So the first point is 7, 7 plus 7.5 upon 2. Here it is coming at 7.16. Z4 will be again 7, first point is 7, second point is 7.5. So 7 plus 7.5 upon 2, which will be 7.25. Similarly calculate Z5, so which is 7.5 plus 8 plus 7.5 divided by 2. No, there will not be 3 points, only one, 7.5, and this is 8. I'm sorry, this 7.5 will not come, and which will be 15.5 by 2, so we'll be given 7.75. Z6 will be, again this is triangle, so the first point is 8, second point is 8, third point is 9. So 8 plus 8 plus 9 upon 3, which is 8.33. So now I know the values of zi and I know the area of each sub fuzzy set. So what I will do to calculate this crisp value z asterisk, I will multiply z1 into mu c bar of z1 plus z2 into mu c bar of z2 plus z3 into mu c bar of z3, like this, divided by mu c bar of z1 plus mu c bar of z2, etc. up to mu c bar of z6. So this will be mu c bar of z1, z2, all these are the areas of subregion, and then I will write this equal to 0.5 into area is 0.5, z1 is 2.3. so basically, okay, I can write interchangeably 2.3 into 0.5 plus second is z2 is 5, a2 is 2, so it is 5 into 2 plus z3 is 7.16, a3 is 0.05, so 7.16 into 0.05, z4 is 7.25 into a4 is 0.15, then z5 is 7.75 into 0.15, then z6 is 8 point, this is basically 8.33, so 8.33 multiplied with a6 is 0.15 and divided by the area of each subregion, which is mu c bar of z1, or I will write a1 plus a3 plus a2 plus a4 plus a5 plus a6, and if I will solve, I will get this is 5.008. so from that, whatever the resultant I got it, okay, and if I'll convert this into crisp number, so I'll get it only one crisp number, and which is 5.08. so this is my resultant. Okay, so this way you can convert this whole fuzzified form into crisp form. Then next is center of sum. Just a minute. Next is center of sum, and this is basically also most common method generally people are using. And here if there is overlapping area, then we have to count twice. It is same as of what we have seen previously. So that is z asterisk, that can be calculated using slight change in the form, which will be I is equal to 1 to capital N, where capital N, let me call it at the number of fuzzy variables, zi multiply with k is equal to 1 to small n, where small n, let's say number of fuzzy sets, where I will write mu a bar k into zi and divided by the normalized form. So basically I is equal to 1 to capital N, number of fuzzy variables, into number of fuzzy sets, and it will be mu a bar k zi. In the same form, small change is there. Instead of z into mu c bar of z, I have there, what is there? There is a change in the multiplication. Okay, whereas small n indicate the number of fuzzy sets, and capital N will be giving me the number of fuzzy variables. Okay, this also I can write into the form of zi into ai divided by addition of all areas. This is also center of sum. So this is center zi is my center of area. K will be, let's say I will vary from 1 to k, so k will be number of rules which have been evaluated, and ai will be your membership function. Okay, so suppose I got the aggregated fuzzy set from the Mamdani model like this. One, two, three, 4, 5, 6, 7, let's say 8 and 9. Somewhat same example. Suppose this is 0.5 and okay, then straight line, then 7 to 8. Suppose this is my trapezoid form. Again from 3 to 4, like this, then 4 to, let's say, up to 8, and from 8 to 9. Okay, so with this two resultant forms I got after the rules evaluated. So this is 0.3, let us take it. Now here let me take one A1 fuzzy set as one trapezoid, and second will be A2 as a one trapezoid. Okay, and from that how to convert it into fuzzified form? This is very simple. Calculate the areas and calculate the center of each area. So consider A1 is the area of fuzzy set C1, and C2 is the fuzzy set, A2 is the fuzzy set obtained from C2. So what is C1 and C2? C1 obtained from one rule and C2 obtained from other rule. So if we'll augment or aggregate, we will get it this area, like what we have seen for the Mamdani fuzzy model for two rules and two antecedents. So there, instead of triangular, what it was like your Gaussian, trapped Gaussian. Okay. not trapped, clipped Gaussian, I'm sorry. Okay, so now let us calculate area. So we know this is the trapezoid, and for the trapezoid, what is the area? Suppose this is A, this is B, this is H. So this area can be obtained using half into A plus B into H. So, okay. So this is very simple. A1 can be calculated using half into A is how much? 1, 2, 3, 4, and B is 1, 2, 8, means it is 7 plus 4 into height is 0.5, and this comes out to be 2.75. Similarly, calculate the area for next trapezoid C2, and this will be A2 is now 1, 2, 3, 4. Okay, half into 4 plus this is 1, 2, 3, 4, 5, 6. Height will be 0.3. So if you solve, you will get 1.5. Now similarly calculate the center for each area. So let me write this Z1 and Z2. Okay, so centers can be computed for fuzzy set is simply this is 1 point and this is second point. So 7 plus 3 upon 2. So Z1 can be calculated as 7 plus 3 upon 2, which will be 5, and for C2 center will be 4 plus 8 upon 2, which will be 6. Okay. So with this information you will get the crisp value Z bar will be equal to A1 into Z1 plus A2 into Z2 upon A1 plus A2, where Z1, Z2 are the centers, and that if you substitute value 2.75 into 5 plus 1.5 into 6 upon 2.75 plus 1.5, it gives me 5.35. So somewhere here will be your center of sum. Now let us see the next method called center of area. This was center of sum. Now let us see how can we obtain using third method called center of area or bisector area of method. So that is short form is BOA. So in this, basically this method is used to calculate the position under the curve where the area on both sides are equal. So basically what bisector area of method, it generates the action which will partition the total area into two regions with same area, you can say. Suppose the resultant, I got it like this. Something like this. Okay, or it has been, what you can say, clipped by like this. So I have to find out the point from where, suppose this is my point Z's asterisk, and say this is my one point alpha, other point is beta. Okay, so that it will partition this curve into equal regions with equal area. Okay, so what will happen, I have to find out this point such that if I'll take it the area from Z, from let's say this alpha point to this Z asterisk, and say this is my mu c bar. So this mu c bar of Z dz, this should be equal to Z asterisk to beta, that is mu c bar of Z dz. Okay, so this Z asterisk will be the vertical line which will partition the region between alpha to beta, okay, with same area. So this is called the bisector area of method. Then next method, let me give the name fourth as weighted average method. So here what can be done, this method is basically is valued for the fuzzy set with symmetrical outputs. Okay, so symmetrical output or symmetrical membership function, and it will produce the result which very close to center of area method. Also, this weighted average method is basically less computationally intensive, and here each membership value or each membership function will be weighted by its maximum membership value. So the defuzzified value can be written as z asterisk will be equal to same addition of z into mu c bar of z over area of all mu c bar of z. This is basically algebraic summation. That is how, let us say, this z will be the element where I'll get it the maximum mu c bar z. How? Let us see. So suppose I have got the situation where I am getting this as a resultant membership function. Now instead of trapezoidal, let me take it triangular. Suppose let me start with this, let us take it some value instead of taking 0. So suppose it's like this, and let me start with 50, 60, 70, then say 80, 90, somewhere 100. This is some value 0.6. Then again from 60 to 80 I have other membership function. From 70 to 90 I have like this. Say this value is again less than that of it. Suppose let us say this is equal. Okay, so suppose this is 0.4 and say this is 0.2 and this is also suppose 0.2. Okay, so what are the elements corresponding to maximum membership function here? So for this, what is the maximum membership function? Let us assume it is triangular. So the elements, let me write like this. Suppose this is my P. For this, what is the maximum membership function? 0.6. Suppose this is my point P. At Q point, what is the membership? 0.4. One more point here, what is the membership function? This point is, let's say, R is the point where I am getting maximum 0.2. S I am getting, say this is my S point, 0.2. let's say one more T where I am getting 0. Okay, so now how to obtain the Z asterisk? That is simply the point where I am getting the maximum membership function. That is, this Z is the point where I am getting maximum membership function. This is basically in the method is. Okay, so here each membership function, that is each membership function which is maximum membership function, will be weighted by its point or its element, you can say. So that Z asterisk will be, P is how much? 60 at 0.6. So it will be Z is 60 and maximum membership function is 0.6. What is Z for this next membership function? 70. So 70 into maximum membership function is 0.4. What is next? At 80, what is the membership function is 0.2. 90, what is the membership function? 0.2 plus 100, what is the membership function? Maximum membership function 0, and divided by all the maximum membership values. 0.6 plus 0.4 plus 0.2 plus 0.2 plus 0. So overall it will give 70. So this is my crisp value. Okay, so this way this weighted average method works. Then next we'll see the maximum methods also. Maxima methods. So this also can be partitioned into three ways. That is, first I can categorize as first of maxima, then next I can categorize as last of maxima. All these are methods basically. Then third I can categorize as mean of maxima. So first, let's say first of maxima, how to obtain. So here what we have to do, we have to determine the smallest value of domain. Domain means your independent variable, where I'll get it the maximum membership value. Basically it is the smallest value of independent variable where I'm getting the maximum membership function. That is how, suppose the resultant evaluated consequence is like this. For this z, some mu bar of z, and I got say 2, 3, 4, 5, something like 6. 2, 2, 3 I have this, 3 to 4 something like this, then 4 to 5 again like this, and 5 to 6 something like this. So this is my suppose resultant consequence. Now from that, if I would like to obtain the crisp value using this maxima method, then how to do it? Okay, so here first of maxima, what it said, it will say that you find out the smallest value of domain. Domain is nothing but this independent variable, so where I'm getting the maximum membership function. So first is at 0.3 I'm getting the maximum membership function, so this will be your simply z bar, which is very simple. Okay, so first of maxima is very simple. You find out the smallest value of independent variable where I'll get it the maximum membership value. Then if I'm saying second, that is last of maxima, what does it mean? It is the value where I am able to determine the largest value of domain where I am getting the maximum membership function. So here what is the last value? This is my last value, somewhere here, suppose 4.5 I am saying. So from this last of maxima I may get it z asterisk as 4.5. okay, and using mean of maxima, it may happen that I may get it so many maxima values. Okay, so I may have more than one elements which will be having the maximum membership function. So how to do that? So suppose got it like this, so all are equal. Suppose let's say 0.9 is the maximum. So suppose here I have got it maximum, here also I have got it maximum, here also I got it maximum. So how to find out the z asterisk? It will be simply addition of all zi points where I am getting the maximum divided by the cardinality. Okay, so what is the cardinality here? How many values? 3 values. So zi will be 3 plus 4 plus 5, divide the cardinality, and this will be 3. So whatever the value you will get it, which will be giving me the mean of maximum. Okay, so here you can find out that from first of maxima I am getting z is equal to 3. If I am using last of maxima I am getting 4.5. If I am using mean of maxima I am getting something like this. Okay, which is how much? 712 by 3, which is 4. Okay, so which value I should take? Okay, so if you will get it such kind of different values, best way, go with the statistical approach, take the average of 2. It may give you the correct value, or some kind of accuracy you may achieve it. Okay, so with this, there are ample of methods are available in the literature for the defuzzification. If you want, you can search the latest methods and you can apply it also. Okay, fine. So this way you can convert the fuzzified form into defuzzified form, that is into defuzzified form means into crisp form, and with that number now you will be able to know what actually or which value of controlled variable you want. Okay, so with this we stop here. Next class we will see the fuzzy inference system with one demo example to design the fuzzy logic controller. Thank you.